So today we finished up the proof that the medians, the three medians of a triangle, are concurrent, that they meet at a common point. And the first element in that proof, and really a lot of the work of that proof is carried right here, is lemma 2.4.3, showing that when two medians of a triangle intersect, they do so at a point that trisects each median. And so that proof begins by sketching a triangle ABC and drawing in just two medians. So here we drew in the median BE, we drew in the median CF. And in doing so, we decide that E and F are respectively the midpoints of the corresponding sides. And then we sketch in the median, the midline that goes from E to F. That's this one right here. And at that point, we invoked the midline theorem. And we applied the midline theorem to the triangle ABC. And the midline theorem applied to the triangle ABC lets us conclude, because we've adjoined the midpoints of two sides, that that midline is parallel to the third side, BC, and also that its length is half the length of BC. So parallel and half the length, that's the content of the midline theorem. But then comes the real innovative part of this proof, is that the prover looks at this diagram and says, well, hey, there's another triangle in the same figure that also has BC as one of its sides, namely the triangle BGC. And so the author of the proof says, well, why don't we try applying the midline theorem to that triangle as well, and let's see what happens, because that's going to give us a link between BC, another link between BC and FE. So applying the midline theorem to that triangle requires us to bisect each of those sides with points that we call P and Q. And because those bisect their corresponding segments, we get that BP is equal to PG and that CQ is equal to QG. So we get another bisection. And when we sketch the midline of that triangle, we again apply the midline theorem to conclude that that segment is parallel to BC, and also that its length is half the length of BC. But BC then provides that link to show us that both of the midlines that we drew, even though they were midlines in different triangles, must be congruent to one another because their lengths are both respectively equal to half of BC. Because BC was that common side in our two triangles that we invoked the midline theorem with. And so what we end up with is this pair of sides, FE and PQ, that are not only parallel because of the midline theorem, but they're also congruent because of the midline theorem applied to those two different triangles. And that means that we have here a quadrilateral, FEPQ, in which one pair of sides, opposite sides, are congruent and parallel. And we saw a theorem, relatively recently, 2.3.5, that tells us any quadrilateral with one pair of opposite congruent parallel sides is necessarily a parallelogram. And so FEPQ is a parallelogram. But we know a lot of other facts about parallelograms as well. Namely, FQ and PE, the diagonals of this parallelogram, bisect one another. According to theorem 2.3.1, we end up returning to that one an awful lot. And since they bisect each other, that means that EG is congruent to PG, and that FG is congruent to QG. But now look what we've done. We've created along the median BE a trisection. The point P and the point G split that segment into thirds, and the same is true along the median CF. The point G and the point Q split that segment into thirds, and that shows what we were trying to show, that any two medians of a triangle at their point of intersection achieve a trisection. That was where the really hard work of the proof that the medians are concurrent was carried. Because then, when we proved that the medians were in fact concurrent, we used lemma 2.4.3 pretty extensively. So how we did that is we drew a triangle ABC and drew in, again, just two medians. We can't draw all three of them in because we don't know that they all intersect at a common point yet, but we can draw two. So we started by drawing in BE and CF, and then calling the point of intersection of those two medians something. We'll call it G. And then what we know about G is that it lies on each of those two medians, and then also, by lemma 2.4.3, that it trisects each of those two medians. So that's one pair of medians that we can say something about. Then we do the same argument, picking a different pair of medians. That's going to require us to draw in the third median, AK, and then also, again, choose one of the medians that we previously chose. Let's say we choose BE. And then the most that we can say here is that those two medians also intersect at a point that we call H, and that H trisects each of those medians by 2.4.3, and it lies on each of the medians as well. And so, of course, what we don't know is we don't know that H and G are the same point. In fact, that's what we're trying to prove. If we can prove H and G are the same point, then that means that all three medians have intersected at a common spot, and therefore they're concurrent. But we have enough information on the board to let us do that. In particular, we know that both G and H lie on the same line segment BE. They both lie on the median BE, because that was our common median in the two different pairs that we chose to intersect. We also know that both G and H have the same distance along that segment to the point E. EG and EH are the same distance because those distances are both equal to 1/3 the distance from E to B. So we have 2 points G and H that are the same distance away from E and which lie along the same segment EB. And therefore, we can conclude they're the same point, and therefore all three medians intersect at a common point of concurrency. Incidentally, even though the author doesn't include this detail in his proof, I think it's worth thinking about why this is a sufficient set of criteria to guarantee that G and H are in fact the same point. How do we know that being the same distance away from a common point and lying on a common line segment guarantees that those 2 points are exactly the same? So let's think about that for just a moment. We know that G and H are the same distance away from E. So EH is equal to EG. Well, that by itself is not enough information to conclude that H and G are the same point. In fact, all that it lets us guarantee is that H and G lie on the same circle whose center is at E. So one way of looking at this is to say that having the same distance from E tells us that H and G lie on the same circle whose center is at E. But as you can see from this diagram, that doesn't rule out the possibility that maybe H is over here, or H is over here, or H is over there, right? Just knowing that the distances are common doesn't tell us that the points are exactly the same. So we need a little bit more information. We also needed to know that they both lied on the same line segment and that one vertex of that line segment was E, right? So the other possibility then is that maybe if I extend this line segment EB out in this way, that now the only possibility we have to rule out is that H is over here and G is at the opposite end of the diameter of this circle from H. But we can rule that out because E, the point from which both G and H are the same distance, drawn to B in a directed fashion from E to B, so going this way, E is the same vertex of that radius, and it's the center of this circle. So they can't be on separate radii, because in fact, if they were on separate radii, we would also see that the distance from H to B would be longer than the distance from G to B. When in fact, we know that the distance from H to B and the distance from G to B both have to be the same because both of them are 2/3 the distance from E to B. So we need H and G to not only be on the same diameter, but to be on the same intersection of the same radius, EB, with this circle. So there are those little details that the author didn't help us to fill in, but they're worth thinking about why this is a sufficient set of criteria for us to guarantee that G and H are in fact the same points.